Appreciate the opportunities to be here. Appreciate the organizers of this event for inviting me. And I do want to talk about unconventional gas lift. And in the year, more than a year since we established this topic, that wasn't the original title I had, but I'm glad to take it and run with it. And we're going to talk about two unconventional things. Okay, first we're going to talk about gas lift as it relates to unconventional wells. Why is it a preferred method? And I'm going to be that bold to say not just one to be considered a preferred method. And how are we going to approach that unconventionally? Not exactly like most people approach gas lift, so not the conventional way. So we'll talk about unconventional gas lift in those two ways. I want to point out this little clipping that I literally tore out of my JPT, where Dave Barry, who's a confirmed pump guy, was basically lamenting that as much as it pains him, he says, by the book, gas lift should be the default lift method for shale wells, which is absolutely true, and I'm going to emphasize that today. Again, Dave is a pump guy, and that's what he's saying, because when you look at the criteria for shale wells, they fit a lot better with gas lift than they do with pumps, and I'm going to talk about why that is. And here's Shauna Noonan. I don't know if any of you know Shauna. She was the president of SPE last year, someone who I know who was kind enough to come to the Artificial Lift Research and Development Council gas lift workshop and to give a talk on that. And I just want to highlight what she said as Oxy's chief artificial lift engineer, that they had 20% of their unconventional production on gas lift at that time in 2017, and that all their new drills they're trying to put gas lift on. And also, that's their preferred method in the Permian Basin. And I want to point out, I'm going to talk about high-pressure gas lift. If you look at the mandrels on this little sketch that's in here, that's not how we do things, and I'll be talking about that. But I also want to mention that Oxy has recently had a very successful pilot of 15 wells with the technique that I'm going to be talking about today. So why gas lift? Well, the main reason is because of gas. So these wells that we're drilling, they're kind of oil wells, but they're more like gas wells in a lot of ways. This is some data I pulled from shaleprofile.com that basically is just showing what initial GOR was and then what it went to over 2 years. And I used 2 full years of data with, before COVID. And that shows that for where we are here, about 1,000. This is on average. I know you have ones that are higher. I know you have some that are lower. And then up to 2,500 GOR. And the amazing thing really to me on this one is the Permian, where you start out at 1,800. You think of the Eagle Ford as gassy, starts out a little gassier, but after 2 years, it's gone to a GOR of 5,000. And so these are very gassy wells. And what does that do? Well, with a horizontal well bore, it's nice when we have vertical wells. We can sump that pump, get it below the gas production interval if we want to. Not so in unconventionals. All the gas has to come by that pump. Now, there's a lot of fancy ways that you can use to try to mitigate that, and those are recommended. But the truth is you still have to handle it. It all has to go either up the annulus or it has to go through the pump. And there's something else that has to go through the pump too, right? All the solids have to go through the pump. Pumps don't like solids. Pumps don't like gas. Gas lift does. Okay, beam pumps, I'll just hit kind of the high points, right? We can't get up to the high rates that most of these shale wells will do. Hopefully they will do. And so that's going to adversely affect your economics. That gas interference is a big problem. There's a lot of high failure rates on this with this method. It's a great method. It's most onshore wells. Previously, conventionally, we've always done with beam pump. But we didn't have these kind of dog legs. We didn't have this kind of gas. We didn't have these kind of solids. And then how about ESPs? Well, they can do the high rates, no doubt about it. But there's also a high failure frequency that tends to go with that, high costs, a lot of lost production. And the truth is, if you look at those pump curves, what you're going to see is there's just a limited flexibility there. Only so much you can do. And so we've got huge changes in rates with these wells over time, and one pump just can't handle it. It's going to have to be changed out. Not the same in a water drive reservoir where the rates stay pretty much the same. And a lot of times people can't get down to the producing bottom hole pressures they want to, so they're going with another lift method. So you're talking 2 lift methods, that's going to cost you money. It's hard to distribute corrosion inhibitor. I know corrosion is a substantial problem here. Hard to get it distributed up and down the well bore with an ESP. And again, we have gas interference. I want to talk technical just a little bit. A couple of things, many people have published on this over the years of gas interference and ESPs. Much good work has been done to increase the amount of gas that can go through at least the whole ESP system with gas separators. But if you look at this example, I think I'm being very liberal in it. Dunbar looked at it, tried to establish what limits the amount of gas, where can we determine what that's going to be at as far as pump intake pressure. And when we look at these two cases, what we see is that, let's say after 2 years where we were talking about a 2,500 GOR, and then you go over to the left and you see you're going to be above 1,000 pounds with the amount of pump intake pressure, where you can expect your pump to start losing head. That doesn't mean it won't pump. It just starts losing head. It starts becoming more unstable. And this is with a 90% gas separator efficiency, okay? This is only 10% going through it. Another way to look at it, you can calculate the gas volume fraction going through with 90% separation, and you look at that and then you say, okay, my ESP stage can handle about 25% gas volume fraction. So after we take that 90% out, this says at 25 GOR, you're still at a minimum of 600 or so pounds intake pressure, and that is going to be about where you're going to end up, and you're going to start having problems. So I'm going to illustrate that with a real well here in just a second. It's food for thought. I'm going to put this up with not much commentary. If you don't know this, 50% of the money that's spent in artificial lift in the world is spent on ESPs. And for those, I see a few smirks. And some of us know why. I'll leave it at that. Gas lift, very small. So what do I mean by an unconventional gas lift method? Well, gas lift is a method of lightening a column of fluid, causing it to flow. You got packers and valves. You're injecting your lift gas in the casing, and usually 900 to 1,200 pounds, somewhere in that range. And it dates back to maybe 1945 when a guy named King developed the type of gas lift valve we use right now. High pressure gas lift is different. It both lightens the column, but also ensures you have enough velocity to actually flow those liquids out of the well. So you can get down to low producing bottom hole pressures. You don't need a packer. You can just inject that gas down either the annulus or tubing. You've only got one point, and that's going to be very deep in the well, which is the most efficient place to put the gas. If you've ever done jetting with coiled tubing, it's just like that. Pressures, maybe it's low, maybe it's high, it just depends on what your well needs. We used to have constraints. We couldn't go to 4,000 plus pounds because the casing was low strength and there weren't compressors that existed, but now that there are, so those limitations are gone. So I'm going to submit that the original gas lift is high-pressure single-point gas lift. They were doing it in 1864 in Pennsylvania with air. So why use this instead of conventional gas lift? Well, really, with conventional gas lift, you're trying to get it 1 point deep in the string to that orifice that's the lowest thing that you can inject through. That's the most efficient thing. That's what you're trying to get to. So in the end, these converge. But high-pressure gas lift has the strengths that we can achieve those high flow rates that are comparable to ESPs, and conventional gas lift can't. It's simpler. We're not running as much equipment downhole. Everything you run below the master valve is a risk. It's a risk to you. It's a potential cost to you. Single point gas lift, high pressure gas lift, very easy to optimize. Not a lot going on down there. Don't have to worry about multi-pointing. And when you read that casing pressure, you're basically at a column of gas. If there's a little bit of friction, you're basically got a window. You've got a window to what is happening at the bottom of that tubing, which you can set deep in the well. For here, I think it's really important. You can distribute that corrosion inhibitor really well. Just atomize it, put it into whichever side you're putting the gas into. It's going to go all the way down to the deepest point in the well. You can run it to the heel if you want, but the deepest point of the well that you want to run that tubing to, and it's distributed across that whole interval, which really helps with corrosion. So, what kind of setup do you need? Well, I've already talked about in the well. It's really simple. You just need a string of tubing. Okay? On the surface, you need some more kit. You've got basically a gas lift setup, but you're going to add a booster, which is shown here in yellow, to get that gas up to high pressures. The concept is really simple. As long as you have enough gas pressure that's equal to a column of fluid at whatever depth you're lifting from, you can lift it. It's that simple. So what that means is, early days, you're going to need a lot of pressure. Later times, you don't need that. You can send that booster home after nominally what people are seeing is 2 to 6 months, and then you've got just a normal gas lift system that you're going to operate with. So it's pretty simple, standard setup with the exception of the booster. So the gentleman who's speaking next to you, Bill Elmer, and I were co-authors on a paper. He's sitting right here, and he's going to be speaking next. But we proposed that this was a huge opportunity for the industry. Brandon Pronk with SM Energy at that time said he wanted to try it, and what we needed is someone to try it and show we could really get these high rates. And what this shows is in the purple, 5,200 barrels of liquid a day is the last point of that. So over 5,000 barrels of liquid per day, up 5.5 by 2 7/8. And that was happening at a bottom hole pressure about 2,800 pounds. We were lifting or injecting gas. It never did go up that high, actually, and kicked right off, but we were injecting about 2,000 pounds. This is the original production from this well. And we're putting about 1.6 million in that well. So he proved, and it aligned with the nodal analysis approach that we had made on this to estimate how much we could make. It proved that that could be accurate and that we indeed could produce these very high rates up these unconventional wells. So in that pilot test that he did, what he did was he compared it to offset wells they were drilling as part of the same program that were running ESPs. These are different. If you're not familiar with nodal analysis, it's showing the productivity in the IPR curve is the dashed black curve, and then the outflow curve, what's happening in the tubing and the rest of the system, are the colored curves. And the fluid rate is on the bottom, and the y-axis is the bottom hole pressure. So this is showing the bottom hole pressure, and the rate that we produced at. And what you see is the ESP. Well, early days on an ESP, what happens? People don't push the rate because they're scared of sand. They're scared they'll fail that ESP early days. And so, in some ways, we can actually exceed that by using high-pressure gas lift. And you see they turn it up over time on the ESP, and the rate actually comes up a little bit, goes down, and then it shows a little bit of advantage versus the dashed red line of the high-pressure gas lift. But this is 100 days, and the IPR change, the inflow performance relationship, the productivity of the well is changing drastically over those 100 days. And what you see is ESP starts out behind about day 25. If the flow line would have been designed correctly on this, we would have been about the same. They undersized it because I think they didn't believe we could make that much out of it. And there's a little bit of an advantage maybe for the ESP. And then what you also see is what I'm talking about this effect with the gas volume fraction. The ESP gets to where it can't suck it down any lower. Okay, it's struggling. But that's not exactly what's happening with the high-pressure gas lift. And so summary is the first 25 days, a little bit of advantage for high-pressure gas lift. The next 75 days, probably a little bit of advantage for the ESP, and after that, the advantage to high-pressure gas lift. I don't want to talk about this and not this from Bill and I's original paper, and it's just showing that in Eagle Ford terms, we could get down to some pretty low producing bottom hole pressures. Here in Bakken, because the surface pressure is a little bit higher, can't get down quite as low, but still very comparable to what you can get with a pump, either beam pump or ESP. And realizing when I'm saying producing bottom hole pressure, I'm talking about at the heel of the well, right? To get that producing bottom hole pressure, you have to add the surface pressure, whatever you have above your pump, and whatever you have below your pump. Okay, this is just for a typical Bakken well. I'm not going to dwell on this. What it shows is you can make, with enough productivity, over 7,000 barrels of liquid a day. As that reservoir pressure comes down, and so this starts out with 6,000 pound reservoir pressure and then comes down. And as you do, of course, the rate drops down. The amount of gas you need for Bakken wells, because it's bigger casing, you need more lift gas, so 2 to 4 million. You see that there's not much difference between 2 to 4 million when lifting these. And this is, again, trying to be a typical, what in my mind, conservative case, 1,000 GOR with more gas would be easier to lift. So let's talk about costs. Well, the costs of an ESP versus high-pressure gas lift, really, they turn on what is the failure rate on the ESP. So if you have long ESP run times, you can see that they converge. But I would think any of you that had 20 months run on an ESP would be really happy. Most people are happy with 12 months in unconventionals, and either you're going to have problems sucking it down any lower, or you just get to rates where it falls off the curve so much that it just won't run much. And so what this says that if you have high failure frequencies with, it gets to be a significant cost advantage. But I do want to address one thing that I know is a problem here with gas lift, which is compression. And that compression needs to be reliable for gas lift to be the solution of choice. And I know that's been a problem. Bill's going to talk about things coming up next that are really going to help with that, and just some basic engineering solutions that he's applied. I do have a data point from an operator in Bakken that was doing both ESPs and high-pressure gas lift, and what they said was, even with the problems, because they hadn't implemented Bill's solutions, even with the problems they had with the compression, that the runtime was at least as high and usually higher than what the ESPs that they were running were. So, some questions I get asked frequently. What about these boosters? Yeah, I'm not going to give a commercial on that, but I'll say that there are two compressor vendors that operate in the Bakken that do have boosters available. What happens after that booster leaves? Okay, well, at that point, you're in good shape as long as you don't let the well fill with liquids. So what we do is we put a shutdown valve on both the tubing and the casing, and when you lose lift gas, you immediately close those valves to conserve that gas. That actually prevents liquids from coming in and fill the well. It leaves you with a lot of energy to kick your well back off, and we haven't had, I personally thought that was going to be a problem. We haven't had any big problem with that. It's still potentially a problem. So without a packer, won't the gas go into the formation? And the answer is just simply no. Now, actually, Brandon in his well with SM Energy had a pressure transducer downhole, and they confirmed the maximum pressures that they saw were only when they shut the well in, not when they had the well open to flow. If you want to inject gas, you have to shut the well in, right? You can't have another path open for flow. It's going to flow because those gas bubbles, gravity demands, they go up, okay, in that liquid environment. So unless you shut it in, it won't go into the formation. So in summary, the characteristics of unconventional wells make them very amenable to gas lift and the preferred solution in most cases. And lifting them unconventionally has significant advantages, and that's high pressure gas lift. And we saw that potentially the cost can be significantly lower than ESPs. Thanks.
Larry, thank you very much. Am I queued up here? Okay. Got a couple questions for you, Larry. First of all, have you seen cases where the high pressure gas lift was not the best lift method for the unconventional wells?
We have a couple of different ones. First, if you have a lot of gas, one evaluation for Permian wells with GORs over 3,000, maybe as high as 10,000 or so. If you have a lot of gas, you become friction limited, and then that extra gas just doesn't help you lower the bottom hole pressure. The other case is actually a Bakken case where they had some wells where they're having great ESP run times, no gas interference because they were very low GOR, very high productivity, and in that case, then actually the ESP looked a little bit better to this operator who does a lot of high pressure gas lift.
Are there cases where you're going to have to supplement the gas stream, or are you producing enough that you don't need to do that?
Yeah, it's a misconception that you need as much gas to lift the well as that injection rate. The way that system works is all you need is enough gas to fuel your compressor and whatever else draws you have of gas on. And so as long as you produce enough gas, which is nominally for a single well type setup, 100 MCF a day or so, as long as you produce that much gas to fuel those compressors and whatever else you have running off that system, then that's all you need. So you don't need a lot of gas to make it work.
I have seen some recent articles where they're talking about injecting in deviated wells where, say, 45, 50 degree deviation, and your gas is starting to ride up the high side of your conduit, either the tubing or annulus, whatever you're producing up. How do you prevent that in this system?
Yeah, it's a challenge. That's why there's not really any advantage to injecting gas down at the really high angles, because as you change, the flow changes completely. As you go to vertical to horizontal, then sweeping that liquid is a problem. And so But even though you can't sweep it efficiently at those really high angles, we're running it usually down to 65 degrees or so. And there's some new work that's coming along that I won't talk about that can help you show where the most efficient place to put that gas is. And, that brings up another question about, do you need some kind of mixer to mix it? And what we've seen is it's working without that, but maybe it would help. We just don't know. I think there's a lot to learn about what the exact angle you put it in at and what you use to mix it, whether there's a significant advantage there.
And the last question I have is, are you actually stripping liquids from your gas stream prior to reinjection?
No, we're not. No, we're not. And Bill is going to talk about why that is a little bit, but we're not stripping the liquids, and you can put it all down there. The good thing is those liquids, we don't have any gas lift valves that we're going to cut out with those liquids, but that's not necessarily the smartest way to do it. And any more questions, Bruce?
No.
So if I could, I'd make one comment is there are hundreds of wells that are being lifted with single point high pressure gas lift at this point. What we're finding is the problem is that the people that are doing it mostly are all that we know of are very happy with it. One major shale operator is doing this. They are not willing to share it because they think it's a competitive advantage. We are willing to share it. And so, it's working really well for a lot of people, but we're the only ones that have published on it. Thanks very much.